Hi, and welcome to my lab report for the first lab of Physics 2211. In this lab, we investigated Newton's second law and how we can apply it to the movement of objects. Newton's second law states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction, unless acted upon by an unbalanced force. This is also known as the momentum principle, as a change in momentum indicates a net force acting upon the system, and therefore no net force acting upon a system indicates no change in momentum, and therefore no change or a constant velocity. We investigated Newton's second law throughout this lab by first recording a video of an object moving at what we perceive to be a constant velocity. We then analyzed the motion of this object using a computer program known as Tracker. We then took the data that we got using Tracker and applied Newton's second law through a computer coding program known as GlowScript to attain a graph of the expected motion of this object when we assumed there was no net force acting upon it. As you can see on the right, Newton's second law states that net force is equal to mass times acceleration, and when there is no net force acting upon an object that has a mass that is not equal to 0, the acceleration must then equal 0. And when acceleration, which is equal to the change in velocity over the change in time, is equal to 0, and change in time is not 0, the change in velocity must be 0, and therefore velocity is constant when there is no net force acting upon a system. This was the video that I used of a tennis ball moving at a constant velocity across a carpeted floor when first inputting my data into Tracker. Tracker used the program to follow the center of the mass of the tennis ball as it was moving along the x-axis in a negative direction in order to obtain data points of its position versus time. The measurement I used as a basis was the 0.0654 meter diameter of the tennis ball. I also altered the coordinate axis so that the x-axis lay along the floor and the ball was moving across the x-axis at a constant y position of 0. Now, there were possible sources of error when using this program, as all plots were plotted by hand, and there was a force I initially applied to the tennis ball to put it in motion at the very beginning of a video. However, I simply used a clip of the middle of the video in order to obtain a constant velocity. I then took the data points of the initial position and the initial time in order to input a velocity into my GlowScript code. As you can see at the very top, the initial velocity was negative 68.2634 meters per second in the x direction. I then applied Newton's second law in the highlighted portion of the code in order to state that when there is no net force acting upon the ball, the velocity is constant. And then I use this velocity to alter the position of the ball to obtain the expected position versus time graph of my tennis ball. Here you can see the observed and predicted position versus time graph, and I will delve more into this later. The red is the predicted position, and the blue is the observed. So the red was taken from GlowScript, and the blue was taken from Tracker. When comparing these graphs, you can see slight differences more towards the end of the graph. The tennis ball was slowing down due to friction, and this friction was not accounted for within the GlowScript code, as we assumed that there was no net force acting upon this tennis ball. We also used the initial velocity within our GlowScript code, and therefore the predicted position versus time graph fits the observed position versus time graph better at the very beginning of the time frame. This also could be due to human error, as I did apply a force in the very beginning of the video, and we assumed net force was 0. However, it possibly was not, and therefore the velocity was not constant. Now, the GlowScript graph does show a linear position versus time graph, which indicates a constant velocity, which is true, as that is what we inputted into the code. However, the observed graph shows a slightly curved position versus time, indicating there was some net force acting upon the tennis ball. Now, the reason for this difference, as I mentioned, we use the initial velocity, as I show calculated at the top of this slide, which was a negative 68.2635 meters per second. However, the final velocity was closer to negative 50 meters per second, which is quite different. Now, what happens if I had flipped the x-axis in Tracker? As you can see, the graphs are very similar. However, they are just going along the position. They're going from a negative position to a positive position. However, the trends are still the same with the linear predicted position and the more curved observed position. Now, what does this mean? Was there actually zero net force applied on the ball? Now, in ideal conditions, there would have been no friction and no force applied, or the force of friction would have equaled the force applied. Therefore, the only forces acting on the ball would have been the force of gravity in the y direction, the negative y direction, and the normal force of the ground against the tennis ball in the positive direction, which would have added up to equal zero net force in ideal conditions. However, we did not have these ideal conditions, and therefore our predicted and observed time graphs differed slightly towards the end of the time frame.